Okay, good morning, class. Looks like we survived a tragic storm in the past couple of days in New Orleans. Looks everybody is doing fine, and glad to see everybody back. So, in today's lecture, we're going to continue to talk about X-ray techniques, and specifically, we're going to talk about X-ray techniques, how it interacts with material. Okay, how do we generate X-ray? So in the last lecture, we begin by talking about what you need to learn about X-ray, right? There's many techniques, areas you can benefit from working with X-ray material. So it's going to be, oh, there's so much mist here. Let me adjust my mask. Okay, better. I can barely see everybody. That's kind of interesting. Okay, let's get back to the topic. So today's lecture, we're going to actually talk some more details that's going to be relevant to X-ray scattering instrument and how we actually understand the X-ray interaction with different material. Specifically, we're going to talk about how we generate X-ray from here, and we're going to go through the instrument, use that as example to discuss our techniques, okay? So we're going to talk about where the X-ray come from, this part. Today's big portion of it is going to talk about this. And we will have some time to talk about when X-ray finish here, come here, how does it interact with material. We're going to talk about X-rays interaction with matter and how it being absorbed and being scattered. Those are two very important parameters for everybody to understand. Then next lecture we're going to talk about how X-ray is detected and how different detector positions, etc., impact our study. But that's going to be much later. So to do X-ray scattering, the first part is you need to generate X-ray, and that's a very simple question, how we generate X-ray, okay? So we're going to do it by using an X-ray tube. It sounds very simple. This is still the similar concept and technique as people did in the early days when you designed this X-ray instrument way back in the early 90s. No differences. So let's go through a little bit basic. This is how the X-ray instrument looks like in the X-ray tube part. So this very long tube has nothing to do with X-ray generation. So the modern technology is pretty simple. Everything is packed in this blue, white-ish box. Manufactured by the company called Xenox. And this is a technique I'm going to discuss later. It's basically a micro-focused X-ray scattering technique, okay? Micro-seal X-ray tube. So it's very tiny, and it's very efficient in generating the X-ray. I want everybody to pay attention to the copper and AKEV. So why this matters? Because it's relevant to how we generate X-ray. A very common one is the copper. Copper is we call it target. So target means you're going to shoot something to the target and target generates some reaction. And in this case, we're shooting electrons. I'll explain a little bit more detail. But copper happens to be generate X-ray at about 8 kilo electron volts. Okay? We also have the controller chiller, etc. below the table. But this part is something we will visually see. And a little bit more discussion about the setup in our lab is where you have two sets of slits. In the front, you basically has X direction and Z direction slits. And you have another pair here. So two pair of slits, they serve only one purpose, is to define how the shape of the beam look like. So imagine this piece looks like a tiny lamp. A desk lamp. Maybe a little bit better. Some of the desk lamp has a directionality, right? You see some of these. But usually they're very poor. They're not lasers. at a long distance, there's still a tiny spot. Later, it has very good directionality and coherence. But in here, X-ray generated is also has directional, but it's not very good. So the slits, which is basically two set of metal blade, they can move up and down to define how big your X-ray beam coming out of it. Okay? And two set of it will help you define a very nice X-ray beam. Okay, so anyone understand this part? This is exactly how it looks like inside the X-ray tube. This applies to our X-ray tube and the band. This also applies to the tool in Dr. Patton's XPS. It's basically the same. Something could be different is actually this part. The piece of metal target can be slightly different. You can put in copper, you can put in silver, you can put in vanadium, you can put in cobalt. All these are being used. Okay? So how this actually works is very simple. You put a high voltage, high current in this part. This is basically a filament. A filament is basically a metal piece strip. When you heat very high, you would generate free electrons, and they have the possibility to leave your metal to be free because of thermal energy. Okay? So now this part, if they leave here, it will be random. You don't have any directionality. However, under the case that if you can apply a very, very high voltage between your electron gun and your target, you can direct these electrons where they go. It's like a super strong magnet. If you apply a high electron fields, you can accelerate these electrons or go into one direction. It's going to be bombarding this copper target. Okay? And then, boom, magic happens when you have high energy electrons hitting your metal target. And the trick is, when you have incident electrons, if they are high enough energy, they have possibility to kick out something we call electrons within your metal material, or any material they would happen, okay? So you could eject and replace an electron within this existing orbital for any material. Well, question?
Just to clarify, this is all happening on the very far left side of the instrument that you showed
Yeah.
in the previous slide?
Yes, yes. So that's where we talk about generation of X-ray. Okay? So, and this could repeat many, many times. And it's probably tens of millions times within your instrument. Okay? So, any question for this part? Nathan?
So just to clarify, the figure on the left is what is happening when the electrons on the right are coming in contact with this copper rod and
Yes.
accelerating that.
Yes.
Those electrons.
Yes.
Okay.
Ben?
What is the heated filament made out of?
I actually do not know. I believe it's something going to be probably high temperature tungsten, something like that. You can heat it at very high temperature, right? But this usually is tiny. So this also applies to other material like electron microscopy. They also use a filament-based technique. In that, it's more a unique compound that can sustain very high temperature. I can get back to you on this question. Very good one. You got me. So the power is not very high. The voltage is very high for this system. You're typically looking at 50 kilovolts. As a reference, the typical power outlet is 110 volts. So this is a really strong field. That's why it can accelerate the electrons at a relatively short time. But the current is low, so that there's only a few milliamps, because that's what happens for these tunneling electrons. So you're talking about a power of 30 watts for the whole system, for the X-ray tube system, okay? Not super high, but it needs to be very high voltage. All right. So there is some fundamental physics happening when you hit accelerated electrons to the metal. This is called Bremsstrahlung-Weiss radiation. So you got a radiation in all directions because of those excited electrons. Okay, so if we go back one slide, you're going to eject this, you're going to create a hole. But this is not stable, as you learn from fundamental chemistry, that this is a low energy lying orbital. So the high energy lying orbital electrons could relax back. So this electrons, hey, there's opening in front of us in a line to get our launch. Let's go there. So this guy gonna move over. And this is low energy, this is high energy. So whenever there is a jump in electron energy states, it's gonna release some portion of its energy, okay? So this electron could jump in, let me make sure I found the next orbital. So this guy could say, I want to go back as well. So they both have the chance. This results in those we called copper K alpha, copper K beta. K is the K orbital. K stands for the inner orbital, okay? And alpha beta is just tells you what is different energy state relaxing from higher orbital. So you will see this causes X-ray intensity versus X-ray energy. And within this Y radiation, you got strips that comes up super high intensity. And these high intensity corresponding to the characteristic of your material. Okay, so copper has K alpha at about 8.04 keV. If you replace with silver, it will be much higher. So you could also purchase X-ray sources with different target. This will result in different characterization energy, which I believe I listed something here. Here is another way to look at how the relaxing of different K alpha. So if you go from the L orbital, relaxing, this is the lowest possible way. So that's why it's going to be the lowest energy. The K beta are going to be slightly higher energy, and you got different orbitals all happening. Okay? So different way to relax the electron. But prerequisition is you need to hit it with super high energy electron to kick away somebody. It's kind of sad. Think about going to the launching or dining hall. Someone in front of you just got it. Then everybody has a chance to jump the line. Not necessarily good in our real life, right? But in quantum mechanics, everybody has a chance to compete if there is opening, okay? So a lot of time we don't want different X-ray energy, so we typically put in some absorbing materials, and you can mask away this portion of it, okay? For example, nickel thin film is used, so the high energy one is all absorbed. I leave this very, very characteristic signals from K alpha. And this now is useful because we want almost as narrow wavelengths as possible, because later on you will learn X-ray wavelengths is dependent on X-ray energy, and the sharper the better. Okay? So those backgrounds you can also put an attenuator to cut away. So in the end, you can get a fairly narrow X-ray energy, and you're ready to do X-ray scattering, etc. Different K alpha line are listed here. So a common one is copper. It's a very good balance of everything. It has a wavelength of 1.54 or 8 keV. They have a conversion there. If you have one higher energy, you can pick silver as target or vanadium. Okay. lower energy, there's also a bunch of other metal you can choose from. So for the instruments we buy, they offers you can pick 2 sources, but you need to pay a hefty upgradation for that. So we only have 1. But in principle, you can have 2 side by side. You can put a motor below it and move it left and right to generate different X-ray energy. And I'll explain in the later part of this class why X-ray energy is important. So in the X-ray scattering, picking a right X-ray energy is important for the application of your experiment. Okay?
Dr. Gu?
Sure, Dina, please.
I was just wondering, is the K alpha typically chosen because it has a higher intensity?
Yes,
Okay.
yes. So in the later on, you will learn in the lab-based technique, the X-ray is limited by we call it flux. Basically, generate how many photons per second. That determines how fast you can measure your experiment. Typically, beta line is weaker than the alpha, so in a lot of time you only use the alpha line. And if you want to use different energy, instead of picking a different line, you go with a different target. Okay? And I'll explain how much energy difference is. Yeah.
If the electron hit the copper for a long time, then what will be destroyed? Why the intensity will be low?
I'm about to come into that. So thank you for asking this question. So as you can see, Lina asked a good question about why we didn't pick one, because we are limited by how much intensity, which is the total peak area. The higher the intensity, actually, the better. Think about photography at the night. Taking the same photo takes tens of seconds or even minutes. If you like astronomy photographer, you need a tripod because you cannot hold the camera steady for a minute also. So same for the X-ray scattering experiment. If you can generate much stronger photon flux, the experiment can be done much quicker. And our flux in our instrument is about 100 million photons per second. It sounds a lot, but it's not, because later on I'll explain to you guys, scattering only happens at a chance about 1 out of a million. So you generated only about a couple hundred scattered photons. And that can be tricky if you only measure a second, because you only have 100 photons. There's background, there are other things. Your statistic is very poor. So we want more photons, better. Generally the case. But I want to ask everybody why we can't generate higher photon using a lab source X-ray. Any guess? Sonia?
Would it be damaging to the human body?
They're always going to be damaging. So we put a good protection, no matter how much flux is there. So in our case, you also see all kind of shielding around it, basically metal pieces. So there's no X-ray can pass this, all going to be absorbed by these shieldings. Any other guess?
Is it the length of the tube?
Not really the reason, but a good guess. Say that again?
We just not have enough power or access to generate enough power?
We could. 30 watts is not a lot. My hairdryer is like 1,500, right? Can do?
What does that have to do with the distance of the detector to your sample?
Neither. All right, I need a creative one. Why can't we generate more X-ray? So let's take a look at the same pair here. Why we cannot generate more X-ray? Ben?
Heat.
Yeah, that's the number one reason. You can only dissipate heat at a certain rate. So if you heat too much, you generate so much heat that your copper gonna melt. Then your target is failed. Okay? So heat is the reason we are limited by this lab sourced X-ray technique. There are several very smart ways people invented to address this problem. So in the early days, it's just a very simple like this. Later on, people invented the rotating anode technique. So you basically put a giant disk here, put a motor here, so you can rotate around. This has a beneficial reason that you can generate larger surface area, basically, through rotation. So you can increase it by a factor of 10 or so, but not great, right? The other part that I haven't mentioned is how you can focus the electron also make a difference, because even though you can generate X-ray, if they're not focused right, if they're all going into random direction, at the end when you slit down, we still lose most of it. So ability, you can focus the electron and focus the X-ray. If you can squeeze them into a smaller area, typically our X-ray beam is about 1 millimeter by 1 millimeter in our lab source. You can generate much higher intensity, okay? So nowadays, the one used in our lab called micro electron CO tube, sealed, S-E-A-L, okay? So it's a focused electron, so your electron not hitting this big area, it's hitting small area. Although you concentrate the energy there, but you can also focus the X-ray out much better within the focused beam and focused optics. So combining two factors, this is already pretty good technique inside our lab. We can generate photons already much higher. Later on, I have a chart to show everybody how much we can generate. So a very genius way to solve this problem is by this company. This is their commercial. So let's watch a second or two. Explains very well. Conventional X-ray tube looks like this.
Are accelerated towards the anode by a high voltage bias. The X-ray brightness can be increased by increasing the electron current. The electron impact point is getting hotter. The X-ray brightness reaches its limit when the electron current finally melts the anode locally. By using a liquid metal anode flowing at a very high speed, melting is no longer a problem. The metal jet anode is continuously regenerated so that the very high electron beam power densities can be handled.
Have you guys seen
The source
chalk?
for X-ray innovation.
You don't need to hear about the last one.
Did you say chalked?
No, I was saying, have everybody seen a chocolate fountain? It's basically the same concept. You keep shooting chocolates. In this case, it's a metal. It's a liquid metal. So there is a certain limitation, but they requires the metal to be alloyed such that there's a few combinations that can be liquid at near the room temperature. Okay. So if you can generate this capability, you can now basically flow them through. They have a bath in below, but now they can Now they can generate a liquid string of your metal jet. It's a clever way. So this is what they showed in their data. So if you look at here, what we are plotting is X-ray flux, basically how intense it is with respect to the energy. So copper alpha is one showed in green light, and the other one, gallium alloy, is the one showed on the right. They showed up at similar energy, but this one is about 10 times higher in flux. It can be a big deal because depends on what sample you measure. If some of the samples are really weak, it literally takes us several hours to measure. So imagine a factor of 10. You can cut down from 2-3 hours to 20 minutes or so, which is quite a big improvement. You can improve your throughput quite a bit, okay? And they can also use different metals to generate different energies as well. So, but they are more costly, about 5 to 6 times more expensive than conventional or even higher. And there requires a lot of maintenance because there's a lot of moving parts, as you can see. Where in the other case, sealed anode is very simple to maintain. But the ultimate game, as I would call it, synchrotron, or more recently, the free electron laser. So let's take a look again. It's slightly different ways people call it. They call it brains, basically divided by the angle and area. So represent how the technique improved over the years. Copper K-alpha rotating anode was here, about 10 to the power of 7. Then here comes into a big boost. This is a million times improvement. This is called the first generation of synchrotron. That's where US has invested to 4 or 5 of them. I'll talk a little bit more detail. With different generation of improvements, you can get super high intensity. This looks like 10 to the power of 24. This is a billion times more bright, which means you can do crazy things. You can look at, there's a trade-off between the brightness and damage. So at that brightness, you're shooting so much high intensity radiation rays into your materials, you can easily damage your material. But at a recent example at the synchrotron, they show you can actually get the scattering before you destroy the material. It's like, which is the chicken first or egg first? People found the scattering happens first before you destroy it. It's a one shot, you destroy material, but you get all the crazy information out of it you can analyze. So let's take a look on the right. So pulse duration is another important part. This talks about how much long each pulse is. This is important if you want to look at fast dynamics. So nanoseconds all the way femtoseconds to even faster rate. So we can track now a single atom's moves using the 3 electron lasers. Okay? So an example of so the question is, how do we generate the synchrotron? It's typically done at a larger facility. It's much bigger than what you saw in a sealed copper tube. So this is an advanced light source in Berkeley lab. I'll explain briefly how they generate it, so get everybody some idea. This is a building about probably about 300 meters in diameter, so not too big. And LINIAC is a basic linear accelerator of those electrons. So you basically like a racetrack in the karate drive a racetrack. So you race these electrons, put it into these booster rings, make them go faster, then goes down to the storage ring. So this ring actually moves those electrons at high speed, go in circles. And whenever you make the electron turns, they're going to generate radiation. Okay, that's a special physics phenomena. Ties into the fundamentals how those synchrotrons generate X-ray. Not necessarily X-ray, it generates a broader spectrum. So let's take a look here. So some of the latest data about how much flux. So if you're complaining about too slow, you can always go to synchrotron, do it at a much faster rate. This is a typical technique called a wiggler in the early days. How you turn an electron is basically apply a strong magnetic field. A wiggler is basically going to wiggle. I can't do that in classroom, you know that, right? But electrons can do it in a pair of magnetic systems, so it can wiggle and generate a radiation fan. So this is some of the techniques people use. The other technique is bending magnets. So this is even simpler. It's just a giant piece of magnets, so make electron to bend at an angle. Okay? Because the electron is charged in the magnetic field. Alien attack. So in the undulator, that's another technique where you look at electron being wiggled by plus minus. So you make it alternating electric field, so you can take turns. And this can generate a very strong X-ray signal, okay? So in a typical synchrotron ring, it's not necessarily a perfect circle. It's basically sectors where you make the electron turns, go straight, turns. These we call insertion device, where you put different undulator bending magnets. And whenever they wiggle, remember they're going to generate all kind of radiations going straight, but here you can separate them in bending magnets. your electrons are going to turn, but your other X-ray, etc., will go straight. So you can build some instrument down here. And if we go back one slide, you will see every single beamline is built like a tangent around this ring, right? So you can see this is one experiment station, this is another one. People trying to pack as many as beamlines within a circle, okay? They're representing 30 different techniques people do using the synchrotron. I'll explain some of the techniques people play with because of the X-ray. So there's several places in the US. Those two where I've been to and work a lot, Berkeley Lab and SLAC is two in the West Coast. You have the Argonne in the Chicago area that also has a synchrotron. Specializing in the much higher energy, so you will see the ring is much, much bigger in the next picture. The other one is Brookhaven National Lab, which is the newer sister generation. They're pushing for coherent X-ray techniques where you can look at X-rays are more coherent. I'll speak a little bit later part what the coherence is. All nice facilities around the country. And I don't want to forget about this. They also have neutrons in the Oak Ridge where they do slightly different things. So this is the ALS, the one we saw diameter about 200-300 meter. And this is argon. This is about, if I remember, a circle is about 1 mile or so, or even bigger. So they're much, much bigger ring, which can use higher energy X-ray. So if you want a high energy X-ray, you go with those facilities. Okay, so back to our beamline. Still quite nice, although lower in flux, but it's more convenient. You don't need to take flight to there or drive there in a couple of hours. You can, in the fundamentals, they're basically the same, okay? So now we understand how to generate X-ray. Here you want to define it. The raw beam is typically much bigger, high intensity in the center, but typically on the order of 3-4 millimeter at here, if you are not slits and down. So we apply 2 slits. This is called a beam defining slits, which defines the beam size. You can imagine this is basically a door or a curtain in your window. How wide you open it defines how much light comes out. Okay, and it has few technology building into it. It's basically using something called scatterless slits, where the slits then scatter. Remember, the metal could do scattering as well. So if you put the metals in the X-ray, it might scatter. So they design some scattering slits, resulting in no scatter. The second one, we call it guard slits, which is cut away further down, filter any non-parallel beams after you defined it here. So after it passes to flight, the X-ray gonna come to here and interact with your sample. That's where a lot of interesting magic happens. We need to understand how X-ray interact with polymer, or more general, how X-ray interact with a given material. So let's take a look at it. So I already mentioned a few things. Incident X-ray is basically another energy form of photon. It's different with electron, okay? Electron is another material, interact slightly different with our matter, but some commonalities share. So when X-ray comes in, I listed it from top to bottom. There's a few different techniques, okay? Or different interaction, I should say. So in this case, I want to think about, everybody think about X-ray is basically a high energy particle. It's shooting in and start to bombard your sample. X-ray doesn't interact with the nucleus, but X-ray interact with your electrons strongly. Okay, so there's a possibility the X-ray, like shooting bullets, it doesn't interact with any of the electrons, then it can pass your target. Nothing happens unhappily passing it. Transmission, okay? It's a concept. So B is where the absorption happens. You could have X-ray doing something as a reverse what we see in the X-ray generation. X-ray generation comes from a high energy electron jump down to low energy, which emit X-ray, but you can also reverse that so that you can excite electrons to high energy, or you can totally eject these electrons. Depend on how much energy you give that. Okay? This is like, this electron is put in a jail, it's gonna escape. But how much energy you give it give its ability, how much it can travel. I'm probably too old to mention a show called not Breaking Bad. There's another called Jailbreak, many years back, talking about a younger brother is trying to rescue the elder brother, so they go into the jail and break out.
Oh yeah, I've seen that. I don't remember what it's called.
Yeah.
It's really good.
It was very, very cool, very surreal. But think about here the same. You give this electron some energy and it's going to escape. Depending on how far it can go, it can do different things. If it's just an absorption in regular different energy opto, we are doing X-ray absorption. Okay, so something very much similar to UV-vis spectroscopy if you think about different orbital energy in HOMO-LUMO, but different, totally different with here, okay? But conceptually they're the same, absorption technique. There are also fluorescence technique, where you have excited high energy electron gonna relax down. It's gonna return some X-ray energy back, partially, typically, and this could be characteristic, and you can use that to do X-ray fluorescence. This X-ray absorption near edge fine structure is called NEXT-AFS. It's very cool. So not only you can understand what elements are, so X-ray absorption measures what elements, because different elements absorb differently. So carbon, fluorine, oxygen, nitrogen, they all have their characteristic energy they absorb for X-ray. So you can use that to identify atoms. XPS is basically similar to those techniques, but a slightly different operation principle. You shoot a high enough X-ray so that you kick out this electron totally in this nucleus. This guy is a true jailbreak, free. It can go anywhere. But you can measure how much energy it lost during the breakthrough process. You know, the incident X-ray, you can measure how much after it's being escaped. So you can correlate to how much energy it needs to escape during the process. That is relevant to XPS. You can use that to quantify material as well. Absorption spectroscopy is everything here. It's not going to be taught in this class because we are focusing on something different, scattering, right? So this is scattering. Scattering means the electron is just a transmission tower. What I mean by transmission tower? The electron didn't move around to any different energy level or escape, it just stayed here. But it's played a role of redirect the X-ray into a different direction. There's two different techniques, subcategory, Rayleigh scattering and Compton scattering. They are slightly different. One is there's no energy loss. The incidence is the same as a scatter beam, so you just change the direction. Compton scattering is more complex, where you have a shift of energy or lose or gain energy during the process, okay? So depending on different technique, there are also imaging technique. I can't forget about that. So you can generate different images using the absorption attenuation rate. So you can do X-ray tomography, etc. The CT is basically X-ray imaging technique. So a synchrotron X-ray has been used in so many different areas to look at surface, interface, bulk structure, morphology, using a bunch of different techniques. So from the top is absorption spectroscopy. You can look at different energy interaction. I won't go into too much detail. The battery community using a lot in X-ray absorption to look at the interaction of interfaces in leasing anode with electrolytes, for example. We use a lot of scattering technique here to look at bulk structure, interfaces, etc. The table, I won't go into too much detail. It is available in the handout. Everybody can take a look. Okay? So I want to emphasize a bit about the trade-off between scattering and absorption. What's the trade-off, I mean? The trade-off, let me see. I should have a better slide. So, okay, here is a reasonable good one. So the incoming X-ray, think about this intensity 0 is how much X-ray before hitting your sample. And the width represents how intense it is. When they interact with your material, it's always going to be absorbed to some degree, no matter what. If your sample weakly absorbs, majority of the X-ray is going to pass it. If the sample strongly absorbs, so a lot of X-ray going to be absorbed by your material, could cause some side effect, depends on how robust your material, if it's going to be radiation damage or heat damage, etc. Okay? So that's why it's important to consider the balance of scattering volume versus absorption. And absorption depends on thickness. This agrees with Beer's law as well. So the thicker the sample, the absorbs it more. Okay? I think everybody learned about this in UV spectroscopy. So there is a trade-off you need to do. If the sample is too thin, there is a drawback. The drawback is we don't have much scattering happen. Okay, if it's really, really thin, tiny paper thin, X-ray all can pass, but the X-ray need to interact with your material to be scattered. If there is not much material, we call it the scattering volume, how much volume X-ray has potential to interact with. If it's too low, you don't have much scatter, everything just pass through, okay? If it's too thick, you go to the other extreme. You have a lot of scattering happen, but at the same time, a lot of absorption. So you don't want, your scattering electrons also has the possibility to be absorbed again. So there's not going to be much signal you can observe. So a good balance needs to be applied to get the optimal thickness. So on-field polymer is typically a few millimeter thickness. This is on the assumption of using our copper target, okay? I'll show a little bit about how different energy correspond to different transmission. That's where energy plays a big role here when you consider your scattering. There's another part which is relevant to a special technique called anomalous X-ray scattering. I might cover in the later part. But for now, all you need to know is transmission. So this is an example of 1 millimeter water. Think about you doing scattering in solution. A millimeter pass, which is how much X-ray need to pass, okay? Using different photon energy. So remember, this is a very weak X-ray. This is a very high energy X-ray. 20 keV is something you can generate in the synchrotron. Using a silver target, you can generate somewhere about 16 keV. Copper target is right here. If you look at the curve, transmission plot versus the energy, you can see at low energy, your water absorbs all of them. Not as there may be a few photons can pass, but if you apply logarithmic scale, you can probably see a little bit change. But technically, you can't do any X-ray scattering here. All the X-ray going to be absorbed, nothing scattered. There's two ways you can do this. Either you use much shorter beam path, which means you need to design a new chamber when you set up that your pass is not 1 millimeter, but 100 microns, or maybe even 1 microns in case of soft X-ray, okay? We're on the order of hundreds of electron volts. 100 nanometer is the range people typically work with. For the energy we use in our lab, which is not too bad, we got about 40% transmission. So this is considered to be around optimal. Okay, you don't want everything passed, so somewhere about 1 divided by E is optimal, so right about here, optimal thickness. You got some absorption, but that's fine, but you can also generate lots of scattering. You can use higher energy, then you can have a higher transmission, or you can work with a thicker sample. Let me give you an example. For example, if someone want to work on realistic sample, that means I want to study, maybe even a crazy example would be very thick polymer sample in packaging and look at how it changes over time. Or even someone might want to look at a very thick plastic for their composites or carbon fiber, etc. If there's filler in it, you're going to continue to lose transmission because they're made of heavy elements. So then you need resort to a high X-ray energy. This is another plot I found for PMMA. This is a 5 millimeter PMMA at about different energy. So 8 keV, we're only transmission about 20%. So that's low. That means you need to cut down your thickness from your PMMA samples down to about a millimeter or two. You can have a better transmission. Okay? And I forgot to put one more slide here is transmission also depends on how heavy your elements are, okay? So the heavier, the higher Z number or atomic number of your material, the stronger attenuation ability it is. What that mean? If you shoot with, let's say, a millimeter, water has a density about 1 made of hydrogen and oxygen. If you have mostly liquid hydrogen, it will be much, much easier to pass, even at the same about 100 micron. There's a website in CXR at LBL. You can simulate different transmission with different materials you're interested to measure. In there, you can find the answer if you're not sure if my new material will have the ability to pass. So coming back, think about attenuation lens for other extreme material like metals. Then that's very hard for X-ray to penetrate them. Metals, even inorganics like silicon oxides, nanoparticles, gold nanoparticles, those attenuate so strong that you probably only need a few micron thickness to absorb most of it. So in those cases, if you stick silica-filled rubber, at 1 millimeter, you're not going to see much X-ray. So you need to consider to attenuate and get it even thinner. Okay, those are some of the considerations you need to have before we go down to the scattering. So with that, I think that's all we need to cover for today. In the next class, we're going to talk about the real show is scattering. And I'll explain how the scattering happens and how does different scattering principles you need to understand. So this part's going to be a little bit challenging. I want to make sure everybody give a read for the textbook related to scattering portion. So what we're going to do is we're going to do scattering from a very simple form to more complex. Start with scattering from a single electrons to a little bit more complicated to atoms, then to molecular, then to a crystal or any structure. So please spend some time. Don't need to be long, maybe an hour or so. Take a read the scattering fundamentals in the book, and this will help you to understand the next class this Thursday. Okay? Any more questions related to X-ray generation and intact with your material, why it's important? Any question? Okay. If no more question, I want to make sure everybody don't stick a 1 centimeter thick sample in the X-ray tube upstairs, because it will not work. Okay. Make sure you understand this. All right. That's it. And thanks everybody.